we start? So good morning. Welcome to the third lecture. So let me just start briefly recapitulating what we have done yesterday. So yesterday I showed you that the homogeneity and isotropy basically fix and constrain your metric of the universe. And so now this is basically uniquely defined. And it's just the FRW spacetime, which is given by here. So this is your maximally symmetric space here. And so at any constant time slice, your metric is homogeneous and isotropic. But I allow these metrics to arbitrarily stretch or shrink with this scale factor A here. And of course, you could have some function of t here, but I can always redefine time so that this is absorbed in dt. So this is without loss of generality. I can always put -1 in dt square. And so this frame is adapted to a co-moving observer. So the observer which is co-moving with the fluid, which sees the homogeneous and isotropic universe. And we also discussed other coordinate systems for this space-time and propagation of photons. And I showed you that on their way, photons actually get redshifted. It's called cosmological redshift. And we also discussed that if you consider random objects in your universe, for example, galaxies, their peculiar velocity, which is the velocity with respect to the co-moving observers, is actually decreasing as the universe expands. So now, if there are no questions to this, let me start a new topic, which is a very interesting topic, and that's of the horizons. So let us consider radio photons. And let me use one of the metrics, one of the coordinates I used yesterday. So we will have our metric ds square is, so that's the conformally rescaled one, minus d eta square, that's our conformal time. And this is our new radio coordinate chi plus sk square d omega square. So now, if it is a photon, of course, this equals to 0. Because it's radial, this guy is 0. So we immediately conclude that d eta square must be equal to plus minus d chi square. Like, so d eta equals to plus minus d chi. Of course, plus or minus depending on whether the photon is coming towards you or whether it's drifting away from you. And let me just remind you how this conformal time is related to normal time. It's just dt over a. Okay, so this is what radial photons will do. So now, let me study what it means. What can we see in our universe, actually? So we know that the universe is expanding. Means that a dot is bigger than 0. And we also define our time coordinate so that it runs from 0 to infinity, 0 being the Big Bang and infinity being whatever we have there. So, and time coordinate goes from 0 to infinity. Okay, so that's one thing we know. So now let me consider for simplicity, and I'll show you that actually this is almost a general case. But at this point, I haven't justified that, so just believe me, or just take this as a simplifying assumption. So let's assume that my scale factor actually behaves as a polynomial in time. Okay, so this will be given by some scale factor at time equal to 0, or at some time, maybe now. And then t over t0 to some power p, which is proportional to t to power p. And I'll take that p is really a constant. So that's my simplifying assumption, bigger than 0. Okay, you will see that for many eras of our universe, this is true. So So whenever the universe is dominated by a single component, for example, by radiation or by matter, this will be true. Okay, so this is like a simplifying assumption, but it's not really simplifying. It's almost true. Okay, so then, if this is true, then I can calculate what the first derivative of A is and what the second derivative of A is. So I'll call this equation 2, and it's A to the derivatives is just proportional to P times P minus 1 T P minus 2. I can also calculate what my conformal time is. It'll be equation 3. I don't have equation 1, okay, so that's stupid. But anyway, let's just call that equation 1. All right, so my conformal time, eta, is just an integral dt over A, which is proportional to t to minus p dt, which is proportional to t1 minus p. Okay, so we integrated a polynomial and we differentiated a polynomial, and that's where all the physics is, actually. Okay, so that's my equation 2 very important and my equation 3 very important. So now let us consider two cases. And so I'll divide my blackboard into two parts. So one, when the universe is so-called decelerating, which means, well, it's expanding, but this expansion is slowing down. Okay, so decelerating universe, which means A double dot is smaller than 0 and accelerating 1. A double dot, which means, well, okay. So now, if you look at equation number 2, so you require that A double dot is smaller than 0, which means that this guy is smaller than 0, but T is positive, right? That means that actually P must be smaller than 1, right? So that's the only way how I can achieve that it is smaller than 0. So from equation number 2, it implies that in this case, this must be true. So maybe let me do the decelerating first, and then. So then equation number 3, what it implies is that if P is smaller than 1, and this is in fact 1 over T to some power, so actually eta goes from 0 to infinity. Okay? So eta belongs to 0 to infinity. Okay? So now I can use my equation 1, which I didn't denote to be equation 1, and I can plot how eta behaves. And so let me use coordinate chi here, and then eta. Let me place us somewhere. So let's say this is eta today. And so we have a person here. Okay. So now from equation 1, you know that if I use coordinates chi and eta, then actually the line travels in 45 degrees. It's d eta is equal to plus minus d chi, right? So the light actually from the past traveled like that. So let's say that we are sitting at chi equal to 0. So you see that anything which was beyond this, let's call this guy chi Big Bang. So let's say this is eta equal to 0 when the Big Bang happened. So you see that you can only receive information at this time from events which happened within this light cone here. So you can never see whatever happened here. So chi baby is called the particle event horizon. Particle or past event horizon. And it means that we cannot see. Of course, this is a function of eta, right? So if I wait a little bit more, I'm here, and then I can see a little bit more of the universe again. So this particle horizon depends on eta. But for a given eta, there are simply things I cannot see at that point. Okay, and that's what's called this particle event horizon. So now to confuse you a little bit more, of course, this is not entirely true because you cannot see beyond the surface of last scattering when the CMB was released. So in fact, actually, until eta CMB was released, your universe is not transparent. So you cannot see beyond this sky, actually. But again, so this will move forward. But so here the universe is completely not transparent, and I cannot see anything there. But okay, nothing to do with the particle event horizon. So now let's look at the same picture, but for the accelerating universe. So now a double dot has to be bigger than 0, which immediately tells you that p must be bigger than 1. So p is bigger than 1. I was trying to save some space here. Okay. So now interesting thing, if you look at the other equation, so if p is bigger than 1, for example 2, I have, well, it's 1 over t to some power. But when you are integrating this guy, it's actually minus sign will be in front of that. So now your eta doesn't grow from 0 to infinity, but it goes from minus infinity till 0. Okay, so eta belongs minus infinity to 0. So now if I want to draw a similar picture, so eta now ends here. So this is the end of eta. 0, and it goes from minus infinity to 0. So if I am somewhere here, eta today, then the only parts of the universe I can ever influence from that moment, it actually have to lie within this light cone. Okay, so I can never influence anything which happens here, right? I could in earlier times, but let's say our civilization is born here, then these guys will never know, right, that we were born here. Okay, so again we have a guy here, and then this is chi equal to 0, and this is chi. It's called chi infinity, which corresponds to chi at t equal to infinity. And this is called future horizon. So for example, if I have an alien here, right? So he will never know if our civilization was born here. He will never know that. Okay. So whenever the universe is decelerating, you have past event horizon. Whenever it's accelerating, you have future event horizon. Simple, right? Okay. So now here comes the, well, very interesting puzzle, which is back in 70s. So there's that puzzle. So what people could measure then was the density of the radiation of CMB, if you want, and they could measure the density of matter. And then solving the Einstein equations, they realized that, well, because they measured this guy and they measured that guy, and of course that determines how A behaves in the end. So based on these two measurements, they concluded that a double dot had to be smaller than 0 for all times. Okay, so that was the measurement, what it gave us. However, this creates a big puzzle. And the puzzle is, well, if you look at that direction in our universe, actually the CMB which comes from that direction is exactly the same temperature, exactly the same as if you look at that direction. But these points there actually could never be in physical contact. So how it is possible that actually there is a correlation between physics here and between physics there? So let me draw a picture of this. So because it's decelerating, is this picture here. So I have eta, I have the Big Bang here at 0, eta equal to 0, which corresponds to Big Bang. We are, at this point, we are here. Eta now. Okay, so let's say I see a galaxy in that direction, which corresponds to this guy. I see a galaxy in that direction, which corresponds to that guy. Okay, so here's my CMB when it was released, eta CMB. And if you look at the path cone of whatever happened here, it's this one. If you look at the path cone of that one, okay, so these are all the events that could influence what's happening here to that star. And these are all the events that could influence what's happening to that galaxy over there, right? But there's no overlap whatsoever. So how is it possible that the physics here is correlated with the physics there? Okay, so that's the puzzle. So why physics correlated? And you know that, well, you don't know, but you will know soon, is that it's correlated to 10 to minus 5. To 10 to minus 5 for CMB, for example. Okay, so how is it possible that the physics here and there are correlated? In fact, if you look at the sky, so only galaxies which you can see within the size of the moon actually could be in the contact. So if I had something which would be very, very close, very, very close, they could have a contact. And so this angle theta corresponds to the size of the moon, approximately. So everything which is beyond could never have been in a contact if this is the right theory. Okay, and so this is a big puzzle, and it was one of the biggest motivations for introducing inflation. And so inflation offers a solution, which you will hopefully discover in your tutorial tomorrow. Okay, so I will just leave you with this puzzle, and you will solve it yourself. So inflation means that before the radiation era, actually there was an era of rapid expansion of the universe, when the universe was actually accelerating. Okay, but that should be enough to solve the puzzle. Questions? All right, so now we discussed all kinematics I wanted to discuss about RW space. So let me move to dynamics. But in some sense, you already studied the dynamics yesterday, although in Newtonian framework. But you will see that it's exactly the same. Well, almost the same. So dynamics. And so now we want, I kept telling you that the universe is expanding, so now let me justify that it is true. So why the universe is expanding? So of course we need to, so at this point we have a metric, but this metric is a solution to Einstein equations, provided I specify what is the source, right? So I need to specify what is the energy momentum tensor, so that I can solve my Einstein equations. So coarse grained, which means I consider these guys on large scales, where the universe is homogeneous and isotropic. Matter content will be described by the most general T mu nu which is consistent with isotropy and homogeneity. Anybody knows what kind of T mu nu I can have? So the most general T mu nu, which corresponds to homogeneity and isotropy. So it is that of the perfect fluid. Okay, so that's the perfect fluid one. So T mu nu equals to P times G mu nu plus rho plus P u mu u nu. That's why you learn about this guy in your general relativity course. So here, u mu is the four velocity of my co-moving observers, or of the fluid if you want. Four velocity of cosmological fluid. So for example, galaxies and whatever, in average. And rho and P are the density and the pressure measured by these observers, so in the rest frame of that fluid. So if actually co-moving is the fluid, I measure certain energy density around me, and I measure certain pressure. And these are precisely what rho and P are, so in the rest frame. Yes?
One question. So T mu nu is a symmetric 0 to tensor, right? So like the metric.
Right.
So if you apply the cosmological principle to the metric, we end up with one undetermined function, which is A. And here we seem to have two functions.
Oh, very good. T mu nu is a...
There's also the conservation law, but this also implies the holds for the metric itself, so it seems to be kind of similar.
But I fixed the frame already in some sense, so maybe it has something to do with the fixing of the frame. It's an interesting question. Let me think about it. Yeah. Very good. Okay, so this is the statement. So now let me introduce one thing which you already encountered yesterday, and that's the critical density. Okay, before that. So now I have T mu nu, I have the metric, and so I can plug it into Einstein equations, and I'll get equations for my scale factor A. And these are called Friedmann equations. So Einstein equations then imply Friedmann equations which you derived in, did you? Almost, right? You just calculated R mu nu or whatever for the Friedmann Robinson space-time in gravitational, but not Friedmann equations. Okay. So anyway, so Friedmann equations, and I'll write them in this form. So h squared, which is our Hubble parameter, equals to 8 pi g Newton over 3 times the energy density, that's rho, minus k over a squared. K is your curvature. That's one of them. And the second one is the continuity equation, rho dot minus 3h rho plus p. And so all of cosmology is about these two equations, basically. So you have seen that the same equations you can derive in this Newtonian framework. The only difference was that you couldn't get this pressure term there. And it's because non-relativistic non-relativistic fields actually don't have pressure. So the pressure is negligible with respect to the energy density. So that's why I couldn't have this plus P here in the Newtonian framework, but that's the only correction to whatever you derived yesterday. Okay, so let me also, this critical density seen yesterday as well. We have done all the work yesterday, so I'm just so rho C, and it's a function of t. So somebody asked me yesterday, it is a function of t, and it's just 3h squared of t, 8 pi g Newton. So it evolves in time in principle, but in terms of this critical density, I can rewrite this equation in a slightly different manner. So plugging h squared from there, so trading h squared for rho c, then this equation gives me that k over a squared equals to 8 pi g Newton over 3 rho minus rho critical. Okay, so that's just the first equation I've written in terms of critical density. So why I'm doing that? So you know that k is a constant which is plus minus 1 or 0. And the question is which one, right? So you want to determine what k is of our universe by measurements. So you try to measure what these guys are. So what it means is that since k is a constant, then if at any time, for example now, rho equals to rho critical, then I already know that k equals to 0, and I measured what our geometry of the universe is. And similarly, if I measure, for example, now that rho is bigger than rho critical, I know that k is plus 1.
Is it obvious that k cannot change?
Well, here it's just a constant, right? But it's, well, you mean, it has like a change of topology of the, well, classically probably, I don't know. Good question. Yeah. Okay, and so similar, so we would know that we are in the flat universe if this is true, for example, now. Okay, so now what is the actual measurement of rho critical at this point, of rho and rho critical? So at this point, people measure that rho is equal to rho critical, well, very, very close to it. So that's the current observation. So it looks like our universe is very, very, very close to flat universe. And this is called flatness puzzle. So the question is there any mechanism which actually tells you that the universe has to be flat? And what is that mechanism, right? So is it really flat, or so maybe k is really plus 1 because it's really this plus 0, 0, 0, 1. But at this point, it seems that we are very, very close to this critical density. Okay. Questions? So now let me justify that really whatever I told you about A is that it behaves like t to some power p is actually true. So cosmic inventory so in order to solve our Feynman equations, well, what is our unknown? So we don't know what A is, but we don't know what rho and P are. So we have 3 unknowns in some sense for 2 equations only. So you need to supplement the system with some additional extra equation, and that's an equation of state. So you have to prescribe how rho behaves in terms of P. Okay, so to solve Feynman equation, supplement equation of state which gives you P as a function of rho. So now it turns out that for many components in the universe, this equation of state is very, very simple. And it's actually that P over rho is a constant. So for many components, you define quantity W, which is the ratio of P over R, P over rho, and it's actually constant. Okay, so if this is true, then we can very easily solve the continuity equation, this equation here. So we have that rho dot, and then I'll have rho plus P is, well, let's say it's 1 plus W times rho. So the continuity equation means that rho dot is the minus 3H 1 plus W times rho. Okay, so which means that rho dot over rho is minus 3, 1 plus W times A dot over A, just using the definition of H. Or, if I integrate this guy, means that rho is proportional to A to minus 3, 1 plus W. Okay, so if the equation of state is that simple, then I can actually solve one of the equations. Questions? It's so very simple, right? Okay. So now let me just discuss some components of the universe, which are typical components. And you can have matter, and you can have radiation, and you can have other things. So let's look at what is the corresponding equation of state. And let's look at how this rho behaves there. So let's create another table. So I'll have a component here. And then I'll have an example. And then I'll have equation of state. Or W. And then I'll have how the density behaves in terms of A. Okay? So the first component you may think about is the standard matter. So for example, galaxies and stuff like that. So matter. So examples are galaxies, you, or me, but also dark matter, for example. Okay. So now equation of state is that if you look at yourself, well, you have some energy density, which is pretty high because mc squared, but the pressure is very, very negligible. It's really tiny pressure if you measure it in SI units or whatever, in natural units. Not in SI units, but in natural units, then the pressure is much smaller than the density. So that's why, actually, you can say that the pressure is basically equal to 0, but the energy density is not, which means W equals to 0. And if I plug W equal to 0 there, you see that the energy density of matter did it as 1 over A cubed. So rho goes like 1 over a cube. Okay, so another possibility is that you have radiation. And so by radiation, I mean basically any relativistic particles. So photons, perhaps neutrinos, gravitons, and whatever. So relativistic particles. So photons, gravitons, neutrinos, maybe. Okay, so now I will show you in maybe tomorrow, maybe the day after tomorrow, that for relativistic particles, rho is just p is just one third of rho. Okay, which you probably know from your electromagnetic course anyway, which means that W is just 1 over 3, and if you plug 1 over 3, then it gives you that the energy density now dilutes as a to the 4. And this interesting chapter is dark energy, sometimes denoted by lambda. And there's a contribution to this dark energy through the vacuum fluctuations, vacuum energy of quantum fields. So now this has very interesting equation of state. Basically it tells you that the pressure is minus the energy density. So it's very, very strange equation of state. Pressure is minus energy density, which means W is minus 1. And if you plug minus 1 into that formula there, something interesting happens. If plus 1 minus 1 is 0. So actually, rho equals to a constant. So rho equals to constant. So this is very interesting, right? Because it means that as the universe expands, the energy density of the dark energy does not dilute. It remains constant. It's like non-conservation of energy, if you want, right? So the bigger the universe is, doesn't matter because the energy density remains constant. So energy is created as you expand the universe. Okay, so it's a very interesting equation of state. Finally, you can also include curvature into. So if you look at this guy here, you see that h squared equals to something times the energy density, and then this guy, k over a squared. So I could, in principle, call this also the energy density of the curvature, rho k, right? So then I know that rho k behaves like 1 over a squared. If you plug it formally there, then you'll find out, so this is k, and so then you'll find out that your equation state is minus 1 over 3 rho. In some sense, and you can just treat them all equally. Just put on the right-hand side rho, and that's it. So okay, so W is equal to minus 1/3, and rho behaves like 1 over a squared, as obvious from that equation. Okay, so these are the typical components which you have in your universe, and you see that for all of them, it's true that P over rho is basically a constant. So now the only time when this is not true is that, for example, when you have, as the universe expands and it's radiation dominated, it becomes at that point matter dominated. So at that point, you know, the energy density, or if you want, this thing is a function of time because you are switching from one epoch to another, in some sense. So that's the only time where this wouldn't be really a constant because you are switching from one to another epoch. Okay, questions? I think it's so simple, right? So let me just write you what I just said. So in reality, you don't have only radiation in your universe, but you have radiation and matter and dark energy and everything. So you have a mixture of all the components. So, but it's always the case that one of the components sort of dominates, and it's because of this 1 over A. So if you look at early times, the thing which is the biggest, which has the biggest energy density is the radiation, because it has 1 over A4. If A is very small, that's something which dominates, right? So history of universe can be divided into epochs. Can be divided into epochs where one component dominated. And then you say, for example, you have matter-dominated epoch. And the reason why you can divide it into these epochs is really that the energy density behaves like 1 over A to some power, and that power is different. So at different times, when A is that size, different components dominate. Okay. At this point, we have dark energy-dominated epoch. So dark energy really dominates at this point. Okay, so that's one remark. Another remark is that if I take the cosmological constant, well, cosmologists don't like this to be something special. And so if you write your Einstein equation, so G mu nu plus lambda G mu nu equals to 8 pi G Newton T mu nu. So they don't want to write it in this way. They rather move this guy to the right-hand side. And they say, well, I can prescribe to my lambda the corresponding energy momentum tensor and treat it as normal matter. Okay, so if I put it on the right-hand side, that means that I can define T mu nu for lambda, which is minus lambda over 8 pi G Newton, G mu nu, and that's the energy momentum tensor of the cosmological constant. And I'll just always have an equation G mu nu equals to 8 pi G Newton T mu nu, where T mu nu also includes cosmological constant. So that's what people like. You seem very unhappy about it. Sorry. Okay. So now, if you look at this equation here, and if you look at the form of the stress energy tensor written over there, you see that lambda also has this form of the perfect fluid, right? So if I identify P equals to minus lambda over 8 pi G Newton, and identify rho minus P, then it's exactly that form, right? So this thing has perfect fluid form, has perfect fluid form, provided I identify rho lambda equals to minus P lambda equals to lambda 8 pi G Newton. And so let me again stress that we show that because rho remains constant, the energy density of this guy does not dilute. It actually remains constant for every time. But it doesn't violate the energy conservation, because energy conservation is nabla mu T mu nu equals to 0. Of course, this T mu nu satisfies that. So that's the relativistic energy conservation, which is satisfied, right? So finally, I told you that there is a contribution to lambda from the vacuum energy. So vacuum energy, which are the crazy fluctuations of quantum fields in your space-time. So definitely contributes to lambda, contribute to the value of lambda. So people try to associate that really, lambda is nothing else than these vacuum fluctuations of quantum fields. And it's predicted by QFT that really this has the right form. So T mu nu of vacuum fluctuations is just rho of vacuum fluctuations times G mu nu. So that's why you can say, well, this is what is predicted by QFT. So you can look at these two, and it seems very similar. Yes?
How do you get that?
From QFT? I haven't derived it, right? Well, ask your QFT guy. Not my business, right? Okay, so this seems very promising, and people try to identify these things, right? Well, what else it can be, right? It must be something which is, yeah. There's nothing else it can be. Right?
Yeah.
No, right? Just a well. Well, it must be same everywhere in the space, right? There's no. So here I have like a preferred u mu u nu, right? But here I don't. So if it is everywhere the same in the space, it must be proportional to g mu nu, in some sense, like just symmetry argument, right? So so this seems very promising, and people thought, well, whatever we observe lambda must be these vacuum fluctuations, but the bit trail is this one, so the numbers are a little bit off. So if you look at the vacuum energy density as predicted by QFT, and if you look whatever is observed for lambda, then this is how well it agrees, right? So there's 120 digits off, right? So it seems, and so this is called old cosmological problem. It's very old, cosmological problem. And people still struggle with this. And then you may already start reading a paper also by Naesh who actually wrote a non-cosmological problem. So you have old and new cosmological problems, but you have also non-cosmological constant problems. So all cosmological constant problems, old cosmological constant problem. And that's why you are so much off. So what can actually, what can kill that contribution of vacuum fluctuations? So in the end, your lambda is so small. That's the problem, right? So SUSY helps a little bit, but not entirely, right? So yeah, so it's a problem. Nobody knows the answer.
So the problem is that the observed one is very small, or the
yes.
vacuum one is very large?
Well, so if QFT is right, this is the prediction. Rho vacuum, you can calculate it.
QFT, you mean the standard model, or you mean some supersymmetric extent?
Well, you can choose any model you like. So if you take standard model, yeah. So this is for standard model. If you take supersymmetry, it's better, but still.
How much better?
Right. I don't know how much better, but better.
60.
Yeah,
10 to the 60.
Yeah, it's better, but not. Yeah, it's not good. But yeah. So lambda is really, really small, and the question is why. Okay. So that's a essay project, right? So maybe you can work on this. So that formula over here.
How do you get rho observed?
Well, you just measure lambda. You measure.
Yeah, how do you do that?
You will do it in your homework. Yeah. So I couldn't. Yeah, you have to do it yourself, right? Then you will believe me. Now, basically, you observe, you measure distances in the universe. Well, you measure how the universe is accelerating, and you measure how the distances change in accelerating universe, and so on. And there was a Nobel Prize awarded for measurement of lambda, if you want. Right? And so in your homework, you will not probably get a Nobel Prize, but you will do the same calculation. Okay. So that formula there, rho is proportional to a to minus 3, 1 plus w, is so important that let me just do it once more, but from a different, so physical derivation, we call derivation of that formula over there. And so you can start with a first law of thermodynamics. And so this is my universe. Let me consider some domain of volume V, and in that domain I have density rho. Okay, so now I write dE equals to dq minus pdv. Another pdv is there. Okay, so now what is true is that there is never a heat flux in the universe through the boundary of the domain. So this guy actually is 0 because there is no neat heat flux. I'll discuss this a little bit more later on, but at this point, it makes sense, right? Why should be some heat flowing inside? Well, every region of the space is the same as any other one, right? So why should there be like a neat flux just to this special region here, right? That shouldn't be. Okay, so then I have that T, now energy is rho times V equals to 0 minus, and then P, again using the trick, is rho times W dV. So now this guy is just d rho V plus rho dV. So now I can collect terms which have dV, and I can collect terms which have d rho. And if you do that, you'll find that d rho over rho equals to minus 1 plus W dV over V. Okay, it's just rearranging that equation, from where I know that rho is proportional to V to 1 plus W minus. And of course, V was a cube, goes like a cube, so this is a to minus 3 1 plus W, which is the same equation here. So here, based on very, very physical argument, you see that this must be true.
But for the curvature, we get a different scaling depending on the dimension that we're in, right? Like it's, oh, sorry, I mean, so it's the same scaling. It does not depend on the curve dimension. It seems to be that the minus 3 always comes in because it's just the number of spatial dimensions we have. So
yeah.
Whereas the one over the k over a squared is for the curvature term is just there in all the dimensions, right?
Well, I thought that we live in 4-dimensional space here. So here, but true, true. So here everything is in 4 dimensions. Okay. Okay, I still have 5 minutes, which is great. So now I can discuss the current cosmological model, which is called lambda CDM model. So lambda, because we need lambda to describe whatever we observe, and this guy stands for cold dark matter. Okay, so that's why it's called lambda CDM model. So, as yesterday in your tutorial, let me introduce density parameter. Density parameter, which is the dimensionless thing. Parameter. And it will be ratio of the actual density of the component I'm considering divided by critical density. So rho I T divided by rho critical T, where this I can be matter, radiation, and all these components I have, lambda, and so on. So people often use this density parameter. And so what is currently observed, so observed now, is the following composition of the universe. Is that omega for matter is 0.32, 0.3. Omega for radiation is not very big, is 9.4 times 10 to minus 5. 10 to minus 5. Omega for lambda is quite big, 0.68. And omega for curvature is only an upper bound on that, and it's more than 0.01. So this is the composition of the content of the universe, if you want. So that's the current content of the universe. So now omega matter can be also split into two parts, and so you have the normal matter like baryons, omega baryons, and that's 0.05. So only 5% of the matter in the universe actually is in baryons, as we is in what we know, right? That's the baryons. That's the okay. So that's baryons. Or if you want normal matter, your standard model, and then you have omega for cold dark matter, which is 0.27. Okay, so now if you look at these numbers, so this is what we really know. So we understand what omega baryons are. So this is dark matter. We understand what the radiation is. We understand the photons, right? We would understand what this guy is. But you know, if you look at what really contributes to the matter content is the dark energy, which you don't understand, and it's the cold dark matter, which you don't understand. So we don't understand our universe. Right? We understand 5% of our universe. Okay. And let me finish with drawing you a graph, which basically is the plot of this thing here. So you have various epochs of domination. So I'll be plotting how a logarithm of rho in some units and logarithm of a in some units. So that's the scale parameter, that's the energy density. So okay, so we know that the slope for radiation is -4. So this would be the radiation. That's slope -4. Then the matter has slope -3. So this would be matter. So this would be where the density of radiation and matter were approximately the same. Then, if you look at the dark energy, then it's just a constant. So this would be dark energy, or lambda. So now we are here. So we are already in the dark energy dominated era. Some other interesting things are where CMB was really somewhere here. So it's already in the matter-dominated part. The CMB was released. And then there is Big Bang nucleosynthesis, which we'll discuss maybe on Friday. And that was in radiation-dominated era and whatever. So whatever the contribution to the density is the biggest, that's the corresponding era. So here, up to here, I will have radiation-dominated era. Here, I will have matter-dominated era. And here, I have lambda-dominated era. Okay? And all of this might have been actually preceded by an inflation-dominated era. Inflation, which would be another sort of like dark energy, but the value of lambda would be much higher there. Okay, so this is the current model, and so let me stop here, and we continue tomorrow.